I would like to discuss a little more on the DC-DC converters, basically bridge DC-DC converters. So let's define the multi-quadrant DC converters. Okay, so it is similar to electrical machines operating as motors or generators. Ever remember for quadrants, we have a similar definition for power electronics devices. So if you are applying a positive voltage and if you are just giving current in one direction to the output, so your converter is working as a source, or you can give like negative voltage and positive current, then it is working as a sink. Or again, you can give some negative voltage and negative voltage, then it can be also other source. Or you can have the second quadrant where you have positive voltage and negative current. So in those ones, in the first quadrant and the third quadrant, you are supplying power, so your converter is working as a source. But in the second and the fourth quadrant, so actually you are using some power, so you cannot connect those things to a passive load like a resistance. But I don't know, maybe you have some kind of PV connected output, or I don't know, maybe you are driving some electrical machines which can operate in 4-quadrant modes. Then also your converter needs to operate as a source and as a sink sometimes. Okay, so let's move on the first one. So there are again, it doesn't have to be just that topology, but that's just an example. So you can have, they are also called type A choppers, type A converters. So here you see a very basic buck converter, so you can control that switch and you can generate some positive voltage and you are giving some positive current. So that means you are operating at your first quadrant. Okay, and let's move to a second quadrant. So here again the diode direction is just changed. Again, those topologies are not specifically important, but I just would like to discuss the different operations. So here we have a back EMF here. So here we can close the circuit. Again, that needs to be some kind of active load, and it is giving some current in that. Actually, the current needs to be in negative direction with respect to that one. So again, the direction is defined like that, but actual current will be flowing in that direction. So that's the type B chopper. Or you can have type C chopper. So this is a half bridge. Okay, so we need to we will see that kind of structure quite a lot in the following weeks. So we have two switches and we have two anti-parallel diodes for each switch. Okay, so this is a 2-quadrant switch. So you can either if you just connect here, you can apply positive voltage, but the current can flow in both directions. Okay, so here you have the first and 4-quadrant converter. Let me go back. So first and 4-quadrant converter. So the current direction is same, but you can generate positive or negative voltages with that one. Okay, how does it work? So you can because of that diodes, you can have that direction of current, and if you apply some voltages to here, you can either have like V1, V in connected to that one. Okay, so here actually those are all just coming one by one, and at the end what we have, and this is the most common one, so this is the full bridge converter. In the full bridge converter you have 4 switches, and of course depending on the load you need to put the anti-parallel diodes as well. This is the simplified circuit. But if you have that kind of converter, you can close S1 and you can close S2 if they are on. You see VD on that side, okay, while the current is flowing in that direction, and you can have the anti-parallel diode, so you can still have the negative current for that one, or you can close S3 and S4, so you can apply a negative voltage with respect to VO, and again the current can be in that direction or in the other direction. So that can be a 4-quadrant converter. So it can operate to generate positive voltages, negative voltages, also operate as a source or as a sink. Okay. So, and again, this is more or less a more realistic one. So these are the anti-parallel diodes that we were talking about. And again, if you are using like MOSFETs, they can have those body diodes intrinsically on the switch as well. But most of the time those body diodes are kind of not fast enough. So specifically you can connect some extra diodes, or if you are using some IGBTs and that kind of things, then you can also have those freewheeling or anti-parallel diodes. Okay, so again, we will see that thing quite a lot. And if you just compare it, let me go back, and if you have a look at that one, that is called half bridge, not as a converter, but the topology, the architecture here, that is half bridge. And if you put two half bridges together, like in this case, so there's one half bridge here, one half bridge here, then your load output is connected between the common points of those half bridges, so that becomes a full bridge. Okay, full bridge is a 4-quadrant DC-DC converter. Why it is important, we will talk about that. So let's discuss the main. Again, there are like different PWM techniques, and we will get into more detailed of those things in the inverters topic. But today I would like to talk about the bipolar voltage switching and unipolar voltage switching. So in the bipolar voltage switching, okay, so let's go back to here. So it is all how you can close those switches. Okay, of course, what you don't want to do, this is a voltage source converter, you don't turn on switch 1 and switch 4 at the same time simultaneously, because that will create a short circuit. We don't want that, but you can turn on S1 and S3, so it will be like a 0 voltage here, or S1 and S2, you will have some voltage here, vice versa. So in the bipolar, okay, as the name suggests, you can have like two voltage positions. So in that converter TA, okay, we have TA, so A is this, you can think like that one is the leg A, and this is our leg B, and the leg A top side switch is called TA plus. So this is the convention of Mohan textbook, but in different books you can have different definitions. And the negative side is TA minus. Okay, so in the bipolar voltage switching, TA and TB are turned on and off together. Okay, so TA plus and TB minus are closed on and off, and TA minus and TB plus are complementary of TA plus and TB minus. So what does it mean? So you close that one. Okay, so let me draw it here, the simplified waveform. That is your load. So this is your VD. So this is TA positive, A negative, B negative, B positive. So either you close that one, okay, once they are closed, is coming like that. So at the output voltage, you see V out is equal to VD. Okay, or let me draw it here. Okay. or let's have a look at the definition. Then TA minus and TP plus are complementary. Complementary means whenever TA is positive, then TAR should be off. Whenever that one is on, that will be off, and vice versa. But of course, those are ideal switches. Normally there needs to be some that time periods. Anyway, so then you close that one and you close that one, and the other ones will be off. Okay, those will be off. So then you will have that kind of voltage, and if this is still VD, so here you can have VD, VO is equal minus VD. Okay, so that means your output can be VD or minus VD. Okay, so if you want to generate some kind of duty cycles between, let's say you have, I don't know, 12 volts at the input voltage, and if you want to generate 10 volts, so at some parts you can apply a negative voltage, and in the average you can get that voltage. So again, that voltage is here. Either it can be measured from A to neutral. Okay, that is our neutral. So again, you can just define the voltage. So the terminal A voltage can be VD or 0 VAN voltage, and you can have the VBM voltage. It can be, again, if that one is close, that is VD or 0. Okay, so AN can be VD and 0, VBN can be VD or 0. So actually, if you combine those things, I mean, this is how the switching, I will talk about the PWM. Just ignore it for now. So what you can have, you have VAM voltage VD, and it is 0, that one is 0. So VAB voltage is equal VAN minus VBN. Okay, if you subtract VD, if you subtract 0, then you will have VD. If you subtract VD from 0, then you will have minus VD. Okay, so the output voltage will be, if this is your VD, and then that will be your minus VD. Okay, so you can have that kind of waveform, and actually you can adjust that period with that period. Okay, and if you want to calculate the average output voltage, so you can take that one averaging with the other one, so you can get an output voltage. So for example, I don't know, let's do that. Let's say VD is, I don't know, 12 volts, and let's say it is for 0.8 of the time. Okay, TA plus and TB minus are on. So for 80% of time, you are applying some VD voltage to the output. Okay, and for 20% of time, you are applying a negative voltage to your output. So for that calculation, let's do that. So you have 12 times 0.8 plus minus 12 volt times 0.2. Okay, this is 9.6 volts. And what is that one? This is minus 2.4 volts. So on average, you will have 7.2 volts average. I mean, it's just a simplification. Of course, there's ripples and other things. But in order to generate like 7.2 volts from a 12 volt supply, if you use that bipolar voltage switching, then you can apply 80% of the time TA plus and TB minus are on, and for 20% of the time TA minus and TB plus will be on. Okay, so how you can control that one, I mean analytically, or not analytically, but using some integrated circuit. If this is your I mean, the idea is, okay, I'm talking about low level control here. Again, you can use, microcontrollers or that kind of things. So this can be your control signal, okay? And that control signal, I mean, in order to generate that PWM signals automatically using some comparators, op-amps, and that kind of things. So I'm talking about that kind of low-level control. You generate some triangular wave, okay, that will be your carrier signal, okay. Then there's some control voltage, and this is the output voltage setting. Okay, probably it will not be clear at that stage, but we will discuss it more detail in the following weeks. So somehow, let's say if I put my control at 0 reference, then whenever my carrier signal is larger than, or my triangular waveform is larger than my control signal, then I am exciting like VB, or I'm using one sequence, and whenever it is less than that one, then I am applying a positive signal. So it is as if, so my triangular waveform is here and my control is there, so I am giving like less voltage, so I need to give more voltage, so let's apply a positive voltage, so I'm applying a VD voltage here, and then my triangular waveform comes in, then it goes above of my voltage setting. So you can say that one can be 0 volts or 7.2 volts. So whenever it goes larger value than that one, so you can say I'm generating too much voltage, let's apply a negative voltage, so it is 0 volts here, VD here, so VAB will be minus VD over this region. So by moving that up and down, you can have a way of generating PWM signals automatically to those switches. So for example, if that control signal is at 0, okay, if V control will be like 0, then you will have 0.5 TS, you are applying VAB will be VD, and for 0.5 TS your VAB will be minus VD, and your average output will be 0, right? So it will be like kind of stupid. So for 50% of the time you will be applying a positive signal, for 50% of time you are applying a negative signal. Okay, so if you somehow increase that voltage, okay, then your positive rates will keep increasing and your negative regions will start reducing, so that way you will end up at a positive voltage. So for example, if you apply a 7.2 volts, so if let's say that voltage will be equal to your, doesn't have to be that way, but same scalar value, if this control signal, okay, you are generating that analog signal, and by using that generated analog signal, you are comparing it to the triangular waveform, and then you end up with 80% positive voltage, 20% negative voltage, so you generate that output voltage. Okay, so the output voltage is VD times the ratio of these two. Again, you don't have to get confused with those things at the moment. We will discuss those things at the inverter. So at the bipolar voltage switching, at the end of the day, at the bipolar voltage switching, you have two voltage levels, as the name suggests, positive voltage or negative voltage. So you can adjust the duty cycle of these things to generate the voltage level that you require. Then you have the unipolar voltage switching, and at the unipolar voltage switching, TA plus and TB plus are controlled separately. Okay, you can have different voltage ratios for those ones, but TA minus and TB minus are complementary of TA plus and TB plus. That is just to prevent any short circuit at the voltage source. So let's have a look at what you can do. So then you have not 2 voltage levels, but you have 3 voltage levels. So how does it work? So let me try to plot it here again. So you have again that system. Okay, so if I close that one and that one, this VO, V out is equal VD. Okay, we already have that one in the bipolar PWM switching. And now I have that one, that one. Okay, so if this is VD, if this is VO, I can write VO is equal VD. Okay, so this is exactly the bipolar switching. So what I can do, and as an extra voltage level, I can close either that one, okay, and that one. You have the VD voltage here, but then you will have that loop and VO will be equal to 0. Or similarly, when it is symmetrical, you can similarly close that one, so we'll have loop here, and in this case VO will be equal to 0. So I can generate VD, I can generate minus VD, and I can generate, I have 2 ways to generate 0 voltage. I can generate 0 voltage as well. So let's have a look at how we can, again, if you are programming some microcontroller, of course, you can write some if-else loops and that kind of things. So here we are talking how you can implement it using really analog electronics, low-level electronics like op-amps and converters. Okay, so here we have the same idea, but instead of using just one reference signal, I have one reference signal. Okay, then I have minus of the reference signal. So for example, if you want to generate 7.2 volts, you apply a 7.2 volts and you apply a minus 7.2 volts. But those volts are not, of course, the voltage levels that you draw a current from. Okay, those are signals, analog signals. So you generate some, I don't know, you can use a voltage division circuit, another op-amp circuit, or like maybe you have a potentiometer where you can adjust the voltage level, that kind of thing. So you can generate that voltage, but you are not drawing current from that voltage level. Instead, you are using that analog signal, putting it to a converter, and it generates PWM signals and your transistors generating some voltage. Then you use that generated PWM output as your power output to generate large voltages or large currents. Okay, so the idea is same. Whenever, this is for A, the first leg, whenever your reference, okay, this is your reference, this is your triangular waveform. Whenever your reference is larger than your triangular waveform, that means I'm like kind of behind. So I need to apply a positive voltage. So you are turning on your positive switch, okay, here. And of course that one is the complementary of the other one, so that one is off. So from A, remember this is point A, this is point B, AN voltage is here. So AN voltage here will be positive. And whenever you are larger than your triangular, whenever your triangular is larger than your reference voltage, then you said, oh, I applied too much voltage, let's close it, and you apply a 0 voltage here, then it goes like that. So if you just control the leg A by using that triangular waveform, which defines your switching frequency and etc., and your control signal, and you can generate some PWM signals, right? Then you control leg B. Okay, this controls leg B, this controls leg A. So you control leg B, using the negative complementary of your control signal. So if this is 7.2 volts, this is minus 7.2 volts. Okay. Then you have a look at that value. Then it is the same thing. Okay. Whenever your voltage level, but in this time it is negative voltage level, whenever that one is larger than your triangular waveform, then you are applying, then it is all the way up, it is negative, so then it is positive. So again, if this is, I don't know, 0.1, if this is 0.9, this will be symmetrical, and I will have 0.1 on period and 0.9 off period. Okay, so phase A and phase B are working with the same duty cycles, but compared to previous case, it was still the same in the previous one. So leg A is on, for example, 80% of time, off 20% of time, and leg B was off for 80% of time and on for 20% of time. So they were, the duty cycles were symmetrical but inverse, but they are happening at the same time. Whenever this is on, that one was off. Whenever this is off, the other one it was on. But with the unipolar voltage switching, okay, so you don't have that kind of relation, but it is kind of interleaved. Okay, they are not happening at the same time, but it is shifted. And how you generate that shift? So you apply a negative control voltage. So let's have a look at if this is VAN and if this is VBN. So let's have a look at VAB voltage, because at the end of the day, that is what our voltage will see. VAN is here, VBN is here, but I would like to see VAB voltage. So in order to have VAB voltage, you need to subtract VAN, you need to subtract VBN from VAN. Okay, so let's have a look at that one. So you have positive VD 0, so positive minus 0, you will have positive voltage. Then you have 0 minus 0, then you will have 0 voltage. Positive minus 0, positive, 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 then you will have 0 voltage. So in this case, okay, in this case, if you just have a look at the output, since here I would like to generate a positive voltage, I generate like VD and I have 0. So instead of going down to negative voltages, so when I am generating some positive output, my output is like, in that term, is like more efficient, because I don't have to deal with the negative voltages. Okay, so this is what you have with VAN minus VBN, but again, this is for positive control voltage. Again, you have the same relation. Okay, so they have, you can do both of those things, they generate the same voltages, but the second one has kind of less ripple. Why? first of all, you don't go down to negative voltages. And secondly, let's have a look at the voltage waveforms here. So this was your PS. Okay, so VIN becomes 1 negative and 1 period for positive. Okay, so if you look at your unipolar here, it is as if the switching frequency is doubled, right? So this is your TS. This is where your full symmetry occurs. Then you start the same relation. So at 1 TS, so you make 0 positive, 0 positive. So it is as if your switching frequency is doubled. So you are running the first leg and second leg like interlead position, so you can get less ripple and you don't generate again much negative voltages at the output. Okay, again you can have a look at the Mohan. I'm not going to solve it here, but this shows the, I mean, this is output voltage divided by VD, so you can generate again, this is a 4-quadrant converter, you can generate positive or negative voltages. Okay, then this is ripple divided by VD. Okay, the ripple at the output voltage. So as you can see with the bipolar PWM, you have a quite large ripple. And again, the worst case is that where you want to generate 0 voltage. In order to generate 0 voltage with the bipolar voltage control, you will have 0.5 on, 0.5 VD and minus VD. So they cancel each other. So V out will be 0, but it will be kind of rubbish. Then you have reduced ripples. However, if you look at the unipolar PWM, then it will have quite less ripple value. Okay, again, I suggest you to have a look at that example. But I would like to show why we are getting into that kind of things and how we can generate that control. What is that triangular waveform that we generate? So but before that, there's also one thing maybe we mentioned in some lectures in voltage source inverters. Okay, so the transistors are not ideal and it takes some time for them to turn off and turn on. And if you just use like TA plus and TA minus, and if you just close on and off those things simultaneously, if you send those signals simultaneously, because the turning off takes some time, the other conductor will get into the conduction and then you can generate a short circuit. So in order to prevent that, we use some dead time. That's also called blanking time. So when one of the switch is closed or one of the switch is turned off, then you just leave some time until you turn on the next one. Okay, that is required. That is required for safe turn off. Okay, and you need to check the data sheet, and in the data sheet you can find the turn off that values. Maybe you need to put some safety factors on top of that one. Maybe there are some suggested dead times for that specific switch, but don't forget that time. At that time, introduce some non-linearity between Vref and output voltage. So let's say you want to generate like 40% duty cycle, but there's like say 2% that time period. So you want to apply a 40% PWM signal, but at the end switches are working at 38% duty cycle. Okay, so pulses shorter than the dead time can be omitted. So for example, sometimes you want to generate a 1% really sharp turn on and off period, but if that specific PWM is shorter than your that time, then you can omit those things, and that will also create some harmonics, as we will see in the coming weeks. Okay, so maybe you can compensate, analytically. You can define a specific lookup table or equations so that you can add your duty cycle. You can give a slightly larger duty cycle. So once you subtract the dead time, then you will have the exact duty cycle that you require. Okay, so that is the general. Maybe I should have shown that schematic at first. So here you have a comparator. Okay, so this is your triangular waveform. It doesn't have to be like that. Again, maybe you are using a digital microcontroller or that kind of things, and again, that doesn't mean you will buy op-amps and triangular waveform generators separately, but most of the integrated circuit controllers have that kind of blocks inside, embedded inside the integrated circuit of that chip. So you can find the details of those things in the datasheet. So the idea is, so here you generate a reference voltage, so you can have, I don't know, let's say this is 5 volts, and there's a potentiometer. So by adjusting a potentiometer, you generate a reference voltage, and that reference voltage is compared with the triangular waveform, and the output will be applied. So you have on and off signals, and output can be applied to your transistor switches, and that transistor switches, let me use that one. So you have a full bridge converter here. Okay, then you have the out. So you apply a positive signal, you get a positive voltage. You can apply a negative voltage, and again that triangular will be going up to some positive voltage and some negative voltage. Okay, so you apply a negative reference voltage, so you can get a negative output voltage. Okay, so that means you can either generate positive 7.2 volts, negative 7.2 volts, depending on the relation between your reference and your carrier signal. So now I think this is like one of the biggest well-kept secrets of the power electronics. So if you have that kind of DC-DC converter, and I'm making that video as an introduction to inverters, okay, what you can do is, instead of applying a constant reference voltage here, if you can just apply a sinusoidal voltage here, then your full bridge will follow that one. Or in other words, all inverters, all AC generators are actually DC-DC generators, which can DC-DC converters, which can operate in 4-quadrant modes, but at every PWM cycle you are changing your reference voltage. So actually it's a DC-DC converter that can work in positive and negative voltages, but you say it to generate some positive, let's say 12 volts here, 8 volts here, 6 volts, I don't know, something like that. Then if you apply a negative reference voltage, then it generates negative voltage. So you apply a triangular waveform, it will try to generate will just try to follow its reference voltage. Okay, so you just, for example, this is how you apply a reference signal, and this is how the PWM of our full bridge converter changes. So at first, so here, like the positive and negative regions are canceling each other. So as it goes up, the positive region gets larger and the negative regions get smaller. So at the peak of that value, you have the maximum positive voltage region and minimum, like really small negative region. Then it comes down. This is for not the unipolar waveform, This is with the bipolar PWM switching. And at the bipolar voltage switching, you can generate either VD or minus VD. So at the zero value, then again they are close to each other. Once you go to negative regions, then you have the negative voltages are much higher than the positive regions. So the output of an inverter is actually like a high frequency square wave, and when you filter out those high frequency components, what you end up is a sinusoid. Okay, so this is how you generate an alternating voltage, alternating current from the DC. Okay, so this is how you generate AC. So it is basically a 4-quadrant DC converter, but you change the reference voltage. Okay, so that's all for this video, and we will don't worry if you got confused at that stage, and we will talk about those things once we get to the inverters. But as we will see, there's really no difference from a DC converter and DC AC converter or inverters. The only difference is how you define the input reference voltage. Okay, thank you.